Hello everyone, I am Sinjit Kui from the National University of Singapore. Today I'll be talking about our recent work, DIDA, Distributed In-Network Defense Architecture Against Amplified Reflection DDoS Attacks. Amplified reflection DDoS attacks are one of the most commonly seen volumetric denial of service attacks. As one of the most notable incidents, which dates back to February 2018, GitHub was hit by the largest ever DDoS attack ever recorded, peaking at 1.3 terabits per second. It was due to misconfigured memcached servers on the internet, where attackers sent forged requests to these servers using spoof IP addresses of GitHub. A few bytes of these requests sent to the vulnerable servers triggered tens of thousands of times bigger response against GitHub. This is a typical example of an amplified reflection attack. Throughout the past few years, more and more incidents related to amplified reflection attacks are also being recorded. Here, we look at more examples of an AR-DDOS attack. In short, amplified reflection attacks are due to connectionless protocols being exploited with spoof requests. Apart from the memcached protocol that I've mentioned in the previous slide, the domain name system, the network time protocol, as well as the simple service discovery protocol are also susceptible to such attacks. Throughout this presentation, I'll be using the DNS amplification attack as the run example. Here, we have some DNS resolvers on the internet. Then we have a target host having the IP of 1.2.3.4. Then we have an attacker with IP 5.6.7.8. The attacker spoofs the IP of the target host and sends forged DNS requests to the open DNS resolvers at a high rate. Here, we note that the attacker are requesting for all records regarding to ISC.org. Unaware of the forged request, the resolvers responds to the request towards the target host. Since all records were requested, the responses are significantly larger than the request. Hence, an amplification factor is achieved. With the enormous responses coming in, the target host network becomes overwhelmed and exhausted, resulting in a complete denial of service. Here, we look at our threat model. We assume an ISP environment. Then we have a victim, customer, or enterprise. There are some public DNS resolvers located on the internet. In order to browse the internet, the victim customer will have to communicate with the public DNS resolvers. Apart from that, there are also some vulnerable public DNS resolvers located on the internet. Then we have an attacker who resides outside of our network. So the attacker aims to saturate the network bandwidth of the victim customer or enterprise. So the attacker coordinates either this globally distributed host or using her own system to send a huge amount of legitimate spoof request DNS queries to the multiple misconfigured DNS resolvers on the internet. In return, the server will send amplified DNS responses to the victim, causing the victim's network resources to be exhausted, resulting in a denial of service. There are several factors on why defending against amplified reflection attacks is difficult. Firstly, there are ubiquitous weapons on the internet. Secondly, for an attacker to launch an attack, minimum effort is required. And thirdly, it is inherently difficult to distinguish attack traffic versus benign traffic. The victim would be aware when he or she is under attack. However, mitigation requires collaborative effort from the service provider or at the autonomous system level. This induces a delay in response time. Hence, the attacker's aim to degrade the service is achieved. For factor number 1 and number 2, there's nothing much a victim ISP can do since they are located outside of the network. Hence, what they can do is to focus on distinguishing malicious traffic in order to protect their networks. This will be our focus today. Before we go into how we can defend against AR-DDoS attacks, we will look at two existing approaches on how ISPs deal with DDoS attacks currently. Firstly, over-provisioning, which basically means to have bigger pipes to absorb attacks. However, this is a temporary solution as it does not scale well. This is due to the fact that there will always be the threat of a larger attack. That aside, this is an expensive solution. Besides over-provisioning, then we have scrubbing. So ISPs today either do scrubbing on-premise or in the cloud. However, this induces additional routing complexity. In addition, in order for scrubbing to be effective, connection tracking needs to be done. Therefore, there is a need to tag ingress and egress traffic accordingly in order to perform stateful inspections. This induces additional latency. Besides, if scrubbing is done on the cloud, there are also privacy concerns that needs to be taken into account. How can we identify and attribute an amplified reflection DDoS attack? The solution is to look at the responses and requests. If one is getting unsolicited responses, then he or she is under an attack. With that property in mind, in this work, we aim to achieve the following. Firstly, is to achieve network-wide AR-DDoS detection and mitigation. This is done through network-wide connection tracking. Secondly, we want to have minimal response time. In order to have minimal response time, we need to reduce the control plane overhead close to zero. This is realized through piggybacking on existing production traffic. And lastly, we want to avoid third-party solutions such as scrubbing in order to have a cost-effective solution. More about minimizing response time. So in order to best achieve that is to do it in network. In order to do it in network, then we would require custom packet processing logic at the data plane level. So how can we achieve that? We leverage on programmable data planes as a basis in formulating our solution. As an example, the notable piece of architecture is shown here. On both ends, there is the programmable parser and the programmable deparser. In between, there is the programmable match action pipeline. This is where we get to define the tables as well as our custom packet processing logic. Then for each stage in the pipeline, there are per stage registers. This is where we store information related to states or counters. Now, leveraging on data plane programmability, let us look at some Strawman solutions. Here, we look at Strawman Solution 1, where we replace the border routers with PISA switches. Each of them will be keeping track of requests and responses in order to perform filtering. However, due to the possibility that different routing policy and decision being made at remote networks will result in different paths taken by the requests and responses. So for this example, the request for the victim left through border 1 and the responses returned through border 2. So border 2 would see a larger number of responses as compared to requests. It seems like they are unsolicited. Should border 2 drop them? The same applies for border 3. How can border 3 tell if they were indeed unsolicited responses? Next, we look at Strawman Solution 2. Instead of the border routers, we replace the access routers with PISA switches. We keep track of the requests and responses here. It seems that it solves the previous problem in Strawman Solution 1. However, upon the detection of an attack, access 1 would have to notify other routers to block traffic coming from A. Naively, we can get the help of the control plane, but under the attack, the control plane would be overwhelmed in this case. Apart from that, dropping A on all border routers would cause unnecessary memory usage at border 1 and border 2 specifically, since only border 3 will ever see traffic coming from A. Based on Strawman Solution 1 and 2, we came up with our solution, DIDA. But our DIDA is not DIDA the Goalkeeper. Instead, it is our network keeper. DIDA stands for Distributed In-Network Defense Architecture in defending against AR-DDOS attacks. As an overview, DIDA requires replacing both the access and border routers, with each of them keeping track of the requests and responses respectively. The access and border would work together hand in hand for detection and mitigation. Here, we look at how DIDA keeps track of the queries. Basically, whenever there is a request being made, the access routers would count them. As for the response, it will be counted by the border routers. In this case, it would be border 2. Here, we have a predefined suspicious threshold of 10. Anything more than 10 within the last time period would suggest that the response could be part of an attack. Border 2 would then tag the response packet with a custom header containing the router ID as well as the counts before forwarding it to access 1. Whenever access 1 sees a tag packet, it would have to extract the information inside. Access 1 would then compare it against with the counts inside its table. For this case, the number of responses is equal to the number of requests, so it is not an attack. Access 1 would then strip off the custom header and forwards it normally to the end host. In this case, what happens when there is an attack? An attacker would send spoof requests towards the vulnerable public DNS resolvers. Then, responses will be coming from the vulnerable servers towards the victim. Border 3 would follow a similar process as in the previous slide. So, whenever it sees more than 10 responses coming from A within the last time period, it would then tag the packet with its router ID and accounts. Whenever access 1 sees the tag packet, it would compare the counts. For this case, there were no requests being sent to A at all. Hence, the number of responses would be significantly larger than the number of queries. We can confirm that it is an attack. Once we confirm that an attack is originating from A, then access 1 will need to inform border 3 to drop any incoming traffic coming from A. So access 1 would convert the existing packet into a notification packet before sending it to border 3. Once border 3 sees the notification packet, it would then add A into its in-network ACL. Subsequently, all the traffic coming from A will be dropped, hence mitigating the attack at the network edge. Implementation-wise, DIDA leverages on emerging programmable data planes. This is what enables DIDA to work completely in-network at line rate. We rely on count-in sketches to count the requests and responses. Each of the count-in sketches would only keep track of counts within a predefined time period. This is made possible through keeping track of the timestamps. Apart from that, for the in-network ACL, it is an adapted version of cuckoo hash tables. This is to ensure that there will be no benign traffic being blocked, since it is a false positive free data structure. Lastly, we have two operator definable variables. First is the suspicious threshold. This refers to the number of responses expected within a time period. In early examples, you may have noticed that we have been using 10. And next, we have the tolerable range. This is to accommodate potential packet losses and stale packets. We have implemented DIDA in P4. Here, we look at our evaluation setup. We have a network with one border and access router. Behind the access, there will be an IPv3 server and an IPv3 client. The client will also act as the victim in this case. Outside of the border, which is outside of the network, there will be an attacker. Between the IPv3 server and the IPv3 client, there will be an IPv3 session being established throughout the experiment. So here, we would measure the victim's effective throughput. Then, the attacker would replay a synthetic DNS amplification trace, which consists of 7,000 compromised resolver. The number of 7,000 is based on statistics released by Cloudflare. Outside of the border, we would measure the attack rate coming from the attacker. So when there is an attack, the mitigation mechanism would take place. So the access would be generating notification packets towards the border in order to notify the border to drop specific traffic. Here, we measure the control message overhead. Upon mitigation, we would measure the effective attack rate towards the victim. Now, let us look at the evaluation results. On the 5th second, an attack is launched by the attacker. This is reflected by the line in red. Immediately after the attack, we see a huge dip in terms of the victim's throughput. Since there is an attack, DIDA's detection and mitigation mechanism would take place. Within seconds, we see that the victim's throughput are being restored, as well as the attack rate towards the victim are being decreased. Upon this experiment, we see that up to 99.8% of the attack being detected and mitigated successfully. In addition to that, the control message overhead being generated by the access router to its border tree are negligible, since we can see that only a maximum of 500 kilobits per second are being generated. As a summary, we have proposed a novel distributed architecture for real-time AR-DDOS detection and mitigation, leveraging stateful programmable data planes. Up to 99.8% of the attack was mitigated within seconds. As part of our future work, we plan to implement DIDA on actual hardware, as well as evaluating it with more realistic DDoS scenarios. Thank you very much for your time, and I hope you enjoyed the presentation. Thank you.